everyone, welcome back to lecture series on aerospace propulsion. So in the previous lecture, we were discussing about the velocity triangle, and from the velocity triangle, we derived the equation for temperature rise across a single stage axial flow compressor, and then we made use of the isentropic relation, that is by assuming a process across the axial flow compressor is isentropic. We made use of the isentropic relation to find out what is the pressurized across the equation for pressurized across the single stage axial flow compressor. Okay, so in today's lecture, what we are going to see is that we are going to see what are the design parameter which basically limits the pressurized across the single stage axial flow compressor, and we are going to see in each and every parameter in detail how do they affect the pressurized across a single stage axial flow compressor. Okay. So we have got the equation, right? The pressure ratio or pressure rise across a single stage axial flow compressor is pi stage, that is P03 by P01 is equal to 1 plus, what is this neta st? That is the efficiency, that is isentropic or adiabatic efficiency of an axial flow compressor, which is going to be obviously less than 1 into UCA by CPT01 into tan alpha 2 minus tan alpha 1 or tan beta 1 minus tan beta. Same equation I can write it as 1 plus neta st u CA by CPT01 into tan beta 1 minus tan beta 2 whole power gamma by gamma minus 1. Okay. So from this we can find out what are the design parameter which is going to basically limit the pressure rise. Okay, you see, first is one is neta st, that is efficiency. Okay, that is a fixed value, we can't do much. Here first is UCE. What is your UCE? U, that is speed at which your rotor blade is rotating. And what is your CA? It is the velocity at which the axial component of your absolute velocity at which a flow enters inside your rotor. And then this tan beta 1 minus tan beta 2 or beta 1 minus beta 2, that is how much your flow is being deflected across the rotor blade. Okay, so from this, if I want to see, like if I want to increase the pressure rise across a single stage axial flow compressor, means what I have to do is that I have to combine all these three parameters together. Just by increasing one parameter, I won't be able to get the maximum pressure rise, which we can achieve across a single stage compressor. That is, I need to increase all these three parameters simultaneously if at all I want to achieve the maximum pressure rise across a single stage. Okay, that is, your rotor blade should rotate at maximum possible RPM, and your flow also should enter at maximum absolute velocity, and your flow also has to be deflected to very high angle. So by combining these three together, we will be able to achieve the maximum pressure rise across a single stage axial flow compressor. Okay, now what we are going to see, so we have seen like I need to increase these three simultaneously, but there are parameters which is going to limit. I can't just simply increase my U, or I can't just simply increase my CA, or I can't increase my beta 1 minus beta 2, that is flow deflection, to like an infinite extent, because there are other parameters which is going to limit the increase of this value to very high limits. So what are those parameters which are going to limit these three parameters? I know clearly if I am able to increase the three parameters, I'll get a maximum pressure rise across a single stage. But there are parameters which are going to limit this increase in U, or increase in CA, or increase in beta 1 minus beta 2. What are all those parameters? That's what we are going to discuss in the next section. Okay. You see, so before going to that, you see, your U, if I'm going to take U, that is a speed at which my rotor blade is going to rotate. So when a rotor blade is rotating, the flow is coming with certain high velocity. When the flow is moving over it, what is going to happen? It is going to create a huge amount of stress, right? you have a heel strength, you have a material. Okay, there is a material limitation. So for the given material, if I'm going to increase my U, what is going to happen? The stress acting on my rotor blade is going to increase. Okay, at certain limit, what is going to happen? If it is going to cross the yield limit, you will have the permanent deformation or damage of your compressor blade. So this maximum tensile stress generated on the rotor blade, okay, is basically limiting the speed at which I can rotate my rotor blade. So that maximum tensile stress is limiting the speed. Okay. Now, let's say if I'm going to increase the U and CA, what is going to happen is that when the flow is passing over your rotor blade, we already told you your velocity is being increased. Higher the speed it is rotating, higher velocity increase you will get. But the thing is that if the CA also very high when it enters, when we are going to rotate it, when its Mach number, if it is going to exceed more than 1, what is going to happen? There is going to be a formation of shock wave. You know, once your flow becomes supersonic or sonic, you will have this. You will have the formation of the shock wave. You know, shock wave basically they are non-isentropic. When the flow is passing through the shock wave, what will happen? You will have the total pressure loss. Okay, so in order to prevent this total pressure loss, we have to limit what Mach number or what is the maximum Mach number inside. So where you will have the maximum Mach number is that you will have the maximum Mach number at the tip of your rotor blade. So we have to limit that. If I'm not going to limit, what is going to happen? I will have the formation of shock wave. So this is basically limiting what is the speed at which my rotor blade is going to rotate. At the same time, to what velocity your flow should enter inside your axial flow compressor. Okay. And next one is third one, the flow deflection. So when the flow deflection is higher and higher, you might have seen in the airfoils, when I increase the angle of attack, what will happen? You will have the flow separation problem. The flow separation will lead to stall in your airfoil. Similarly, as you know that your axial flow compressor also made of an airfoil shaped blades. If your flow deflection is very, very high, means you will have the flow separation which will lead to stall of your compressor. So there is a limitation of how much flow deflection you can make across your single axial flow compressor. So all these three parameters are limited by one way or another way. So we are going to see numerically how these parameters are being limited by the other parameters. Okay, let's start with the first parameter, that is U. How does this U or U is limited? We already told you that is the maximum tensile stress generated on your blades. Okay, so that is what we call it as the centrifugal stress generated on your axial flow compressor. This is the one which is going to limit your RPM of your rotor. Okay, so let's say centrifugal stress, if I'm going to take stress generated, basically it is going to depend on what speed it is your rotor blade is rotating, and what is the density of your material, and what is the height of your material. So these three parameters is going to dictate how much amount of centrifugal stress is generated on your rotor blade. And from the experiment, it is found that at the fixed end, basically at the root of your compressor blade, that is rotor blade only, you will have the maximum centrifugal stress. Okay, now we are going to find out what is the centrifugal stress equation, and from that we are going to decide how much should be the speed your compressor can rotate, that is your rotor blade can rotate. Okay, let us take an random airfoil shaped blade. Okay, that is compressor blade. This is basically a root where your blade is fixed on the hub. Okay, and this is the tip of your blade. What is your AH? That is the area of your blade at the root. And what is your AT? Area of your cross-sectional area of your blade at the tip. Okay, what I'm going to do now is that what is your the small area? Okay, that is small blade element dr I'm going to take. In that small element dr, what is the force acting on it? Okay, that is centrifugal force acting on it. I'm going to find out what is the centrifugal force DFC acting on that element I've taken means DFC is equal to omega square R into delta M. Okay, so what is your omega square? That is omega. It is the rotational speed of your rotor blade. What is your R? Your R is the distance from your hub where we have taken this small elemental blade, and the delta M is the mass of the blade which we have taken. Your M delta M is the elemental mass. Okay, so I can find out what is the elemental mass of my blade element which I have taken. That is, what is the equation for your mass? Mass is equal to density into volume. So your delta M is going to be density, that is rho B, that is the blade density. And what is the volume? It is going to be cross sectional area A into what is your height? Our height I have taken it as dr. So A into dr will give you volume. So delta M is equal to rho B into A into dr. Okay, so that is the force on this small elemental blade. I have to find out what is the stress. Okay, so stress, if I want to find out, your stress will be equal to your centrifugal force divided by the area. And I already told you at the root location only we'll have the maximum centrifugal stress. So I can write sigma C max, that is centrifugal force maximum, is equal to force divided by centrifugal force divided by area at the root. Okay, so omega square by A root into integration of this force is basically DFC is elemental force which is acting on that small blade element. I have to find out on the entire blade element how much amount of force is acting. That's why I'm integrating from root to tip. Okay, so R into delta M. So sigma C max is equal to rho B omega square divided by A, that's area at the root location, integration of root to tip R into A into dr. Okay, so from this you can see if I'm going to increase my RPM, the stress, okay, is increasing. That is your sigma stress. Sigma C is directly proportional to omega square. Okay, and similarly, what is the density of our material, and similarly directly proportional to volume. Okay, so higher the blade or lengthier the blade means you will have more stress. Similarly, maximum speed it is going to rotate means you will have the maximum centrifugal stress. So there is a limitation of how much, because we have know the material and we know what is the yield strength of that material. So we can find out what is the maximum stress. Okay, whether by, let's say I'm going to take 10,000 RPM. So for the 10,000 RPM, what is the stress? Whether it is limited, whether it is less than the yield strength or greater than the yield strength, we have to find out. Okay, so this stress generator, centrifugal stress generator, is basically limiting the maximum RPM I can rotate. Okay. Now next is the tip Mach number. Okay, so the Mach number where you will have the maximum tip Mach number is at the first stage, because you know the velocity is equal to omega into r, tip velocity. Okay, so you know that the first blade is the one which is having more height. That means you will have the maximum tip Mach number at the first stage of your rotor. Okay, so we have a different configurations, right? That is constant hub or constant casing or mean radius or constant thickness. There are so many different types of compressor we have. Irrespective of whatever the condition or whatever the type of compressor we are going to have, your first stage is going to have the maximum blade height. That means you will have the maximum tip Mach number at the first stage. So as long as you are able to control the first stage tip Mach number, you can control what is the tip Mach number at the later stages. Okay, so this tip Mach number is going to be depends on what speed you are blade is going to rotate. And what is my inlet velocity? CA. Okay, so we already know there is a limitation on your U because of your centrifugal stress. Okay, at the same time, there is a limitation on U in order to prevent your blade tip Mach number to achieve a certain value. So we don't want our Mach number to achieve supersonic in case of your subsonic compressor. Okay, modern days we have the transonic compressor. There you can get achieve, or we can have a Mach number of maximum 1.2 to 1.3. So that depends on if it is a subsonic compressor, means it should not exceed more than 0.8. Okay, so your tip Mach number is depends on speed and inlet value CA. So how do we control this CA value? Is that by putting the what is, I already told you what is the purpose of your inlet gate fan. By adjusting the inlet gate vane, you can control what is the value of your CA at which it enters inside the first stage of your compressor. Okay, your U is going to be limited because of the maximum centrifugal limit. At the same time, you will be limited in order to prevent your flow from achieving M is equal to more than 1. Okay, so this is the equation for tip Mach number. Tip Mach number is equal to maximum relative velocity divided by what is the speed of sound A. So W1 max, I can write it as root of C1 square, that is from the trigonometric relation, C1 square plus U tip square divided by root of gamma RT. So from this you can see, if the absolute velocity is higher and higher, you will have the higher or maximum tip. So how do I control this tip velocity or Mach number? Is that by introducing the component. How we are able to introduce the component is that by having the inlet gate vane, I can control at what angle my flow will enter inside the first stage of my axial flow compressor. Next is the, see, this is the relation between the maximum Mach number versus what is the inlet velocity. As you can see here, when your inlet velocity is increasing, the Mach number it is going to achieve is basically it is increasing, right? So at let's say if my inlet velocity is 150, it is within the limit. Instead of that, if I'm going to have inlet velocity is 250, you see you have more than Mach number 1.2. So this is basically limiting what is the tip velocity. So you can see here when the inlet velocity, that is C1 absolute velocity, is increased, the Mach number it is going to achieve also is going to be increased. Okay, so that's what I already told you. For the transonic compressor, the acceptable value of maximum Mach number is 1.1, whereas for the turbofans, we can have up to 1.5 to 1.7. Next is the fluid deflection, that is beta 2 minus beta 1 for the rotor, or alpha 3 minus alpha 2 is for the stator. So why this fluid deflection is also limiting parameter is because when I already told you, when what is happening across your rotor blade or stator blade, your pressure is getting increased. Pressure increase means basically it is an adverse pressure gradient. We already know the adverse pressure gradient, that is in the direction of your flow, your pressure is increasing. Okay, so which will lead to flow separation easily. A flow which is having favorable pressure gradient will not separate compared to a flow which is having the adverse pressure gradient. Okay, because here your flow is moving against the high pressure. So if your deflection is higher, means what is going to happen? The diffusion process also will be high, which will lead to the flow to lose this complete momentum and your flow will separate. So once your flow separation happens, means what is going to happen? You will have the so much of vacuum zones, and this vacuum zone, basically your flow will not move. If it is losing its complete momentum, means it will not move to the next stage. It will become a kind of stagnant and it is going to block the incoming flow itself. So what will happen? First you will have the total pressure loss, and next is kind of like a choking like phenomenon, which is basically preventing your flow movement. Because of that, the later stages will have a deficiency in getting the flow, or because of that, your combustion chamber also will lose the pressure supply it is getting. So you will have the reverse flow. So what will happen if you are having a more angle means you will have the stalling of your compressor, which we don't want. That is why how much deflection we can give to the rotor blade or stator blade is also limited because of your stall. So if I want to prevent stall means I should fix my beta 2 minus beta 1 or alpha 3 minus alpha 2 the minimum limit such that you will not have the flow separation problem. Okay, so these are all the three primary parameters which basically limits the pressure rise across a single stage axial flow compressor. Okay, so with this I'll end this today's lecture.
Like, share and subscribe. Hit the bell icon for more updates.